For over 100 years, steam turbines have generated power using water and steam. Over the years, that steam got hotter and more pressurized. It made the turbines more efficient, but also made them big and complicated. Now, here comes a different type of turbine, radically smaller, drastically simpler. These turbines have CO2 running through their veins instead of steam. In today's video, supercritical carbon dioxide turbines, the waterless wonder that may be 10 times smaller than their counterparts. Steam turbines run on the Rankine cycle. In Rankine-based turbines, water is turned into hot pressurized steam inside a boiler. That steam cools and expands when it hits a set of turbine blades. Shenanigans and electricity follow. In the end, we condense the steam back into the liquid water phase so that the party can get started all over again. The Rankine's key trait is that it uses a liquid as the turbine's primary working fluid, with that liquid changing phases to gas and back in a loop. A heat engine's efficiency depends on the temperature differential of the fluid going in and out of said engine. Since the outlet temperature tends to be fixed, we have to raise the inlet temperature. So, to make our turbines more efficient, we, and I mean we as in the human race, not me and you personally, have worked to make the incoming steam hotter. As part of this strategy, we now compress and heat the water beyond its critical limits to make it a supercritical fluid, a weird state of matter with traits of both liquids and gases. Once supercritical, the water turns directly into steam without boiling, letting us heat it up even more. Today's top ultra supercritical turbines have efficiency rates of about 43 to 48%. Utilities want efficient turbines because it means getting more energy for burning the same amount of coal. Since their single biggest operating expense is the cost of the fuel, you want to get the most out of it. One can argue that the Rankine cycle is quite efficient on paper, but achieving those efficiencies in reality can be tricky. After passing through the blades, the steam still has residual energy that can only be recaptured with another set of fan blades. In the end, we can only add so many rows of fan blades until it gets a bit ridiculous. Some Rankine steam turbines have 30-plus stages of very large fan blades. So the Rankine is one of two major philosophies for running a turbine. But as Yoda says, there is another. The second is the Brayton cycle, or Joule cycle as some like to call it. It is the basis of jet engines and the gas-fired turbine. The key aspect of the Brayton is that the working fluid remains in the gas phase throughout the whole cycle. The gas turbine takes in air, compresses it, and then adds the natural gas as fuel. Then we ignite that sucker using a combustor to bring it to a high-energy state. The high-energy air hits the turbine blades, losing pressure and cooling down in the process. After passing the turbine, the hot gas is often expelled out the back like a bad customer. So, the gas-fired turbine is an open-cycle Brayton system. There is a variant of this system called the combined-cycle gas turbine, where the exhaust's residual heat is used as a heat source for an attached Rankine steam turbine to garner yet more efficiency gains. I should also note here that we have a whole rogues gallery of Brayton variants, all with their own trade-offs. The use of gas has certain benefits. With steam turbines, the super hot steam can degrade the metals in the turbine blades due to moisture-induced oxidation and creep, where the steel deforms over time due to extreme stresses. Dry gas is more forgiving on the blades at higher temperatures, and thus, indeed, modern gas turbines can operate with inlet temperatures between 1300 and 1500 degrees Celsius. Such incredibly high inlet temperatures let gas-based Brayton cycle systems operate at higher efficiencies, up to 60%, higher than those of top Rankine-based ultra-supercritical turbines. In addition to the rather common open-cycle Brayton, there is the closed-cycle Brayton, which is a bit rarer. In a closed-cycle Brayton, the gas is compressed and heated up indirectly by some heat source via a heat exchanger. And after passing through the turbine blades, it is sent back to the heat exchanger to extract some heat before being put back into the fold, like how Mufasa tells it in The Circle of Life. A closed-cycle Brayton can use any gas as its working fluid. One of the most closely studied gases is helium. The pluses of helium is that it is safely inert, conducts heat much better than air, and flows cleanly. Helium has serious downsides, however. It has a low molecular weight, which means it easily leaks through shaft seals, imperfect welds, and even small cracks in the casing. Since it is also kinda expensive, we need some extra engineering to keep it sealed. The gas's low density also means it takes quite a bit of energy to compress. Power-hungry gas compressors inflict a considerable penalty on the helium Brayton turbine's real-life efficiency. Hence, to compensate, the helium Brayton system needs a very high inlet temperature of something in the neighborhood of 900 degrees Celsius to achieve efficiency rates comparable to that of top Rankine turbines. Certainly possible for an open-cycle system, but for a closed system, a lot tougher. So despite helium's strong advantages, people have shifted their attentions to carbon dioxide. Carbon dioxide is well studied, particularly since it was used as a coolant for early-era nuclear reactors, so people are familiar with it. It is quite stable at turbine-level temperatures of 1500 degrees Celsius or more. It is also non-toxic, less likely to leak than helium, and is cheap and abundant. Perhaps a bit too abundant nowadays, but yeah. When supercritical, carbon dioxide's fluid density is 50% higher than that of steam. Depending on your assumptions, that implies a turbine to be some 10 times physically smaller than a Rankine cycle turbine due to smaller parts and fewer stages. Another important thing is that carbon dioxide's critical pressure limit of 7.38 megapascals is just about a third that of water. Moreover, carbon dioxide's density rises as it approaches that critical limit, making it more incompressible like a liquid, which is a big deal because it is easier to compress an incompressible liquid than a low-density gas. In Rankine steam turbine systems, pressure is applied with simple water pumps. Since gas compressors, like I said, use so much energy, CO2 getting more liquid-like as pressures approach the critical limit means that the gas compressors can work less. So all in all, a supercritical CO2 turbine can be just as efficient with inlet temperatures of 550 degrees Celsius as a helium Brayton turbine with inlet temperatures of 900 degrees Celsius. The simplest supercritical CO2 Brayton system goes as we talked about earlier. A compressor first compresses the CO2 to near the critical limit. Then the CO2 is heated up. First heated up inside the recuperator with heat from the gas exiting the turbine later on down the line. And then heated up secondly from the primary heat source, nuclear or otherwise, indirectly via a primary heat exchanger. The carbon dioxide then enters the turbine where it expands and cools. The turbine turns the generator, electricity ensues. Now we must recuperate heat from the carbon dioxide exiting the turbine. We send it to the recuperator system to transfer its heat to the gas exiting the compressor. Then it goes back to prepare for the cycle to restart all over again. We call this the simple recuperated supercritical CO2 power cycle. Note how the gas travels in a single flow throughout the cycle. This single flow works and is simple enough, but frankly is not all that efficient because the temperature difference between the gases exiting the compressor and exiting the turbine is not that great. We are not recuperating enough heat. So engineers have developed a variant called the split flow. They split the CO2 gas flow exiting the turbine into two, running the twins through additional components like a compressor to maximize heat recuperation and thus efficiency. There are so many variants. all tailoring the cycle to fit certain applications or circumstances. For instance, they might blend the CO2 with additional gases to tweak the cycle's overall commercial viability. And then, notably, there is the alum cycle, which is an interesting expansion on the concept. In it, we burn natural gas and pure oxygen together to get carbon dioxide. This carbon dioxide is all captured and run through a supercritical CO2 turbine to generate power. After that, the gas is sent to be sequestered. The idea of using supercritical carbon dioxide for a closed-cycle Brayton dates back to 1948. That year, a Swiss industrial engineering firm called Sulzer Brothers filed a patent for a Brayton turbine utilizing supercritical carbon dioxide. They never did anything with it so far that I can find, however. Then in the 1960s, an American engineer at Douglas Aircraft named Ernest Feyer published a series of papers that led him to propose the supercritical power cycle, choosing carbon dioxide as the working fluid. The supercritical power cycle is similar to the Brayton cycle. The carbon dioxide operates throughout the whole system at above its critical limit. To sidestep the challenge of pressurizing carbon dioxide gas, we compress it to near the critical point. Other individuals working on the supercritical cycle, or something like it, in the late 1960s include D.P. Goldstein and G.P. Verkhifker of the Soviet Union, and G. Angelino of Italy. All of their work showed that supercritical CO2 turbines have generally higher thermal efficiencies than existing Rankine steam turbines, anywhere from 48 to 50%, which is an impressively high number. Plus, their smaller size and simpler designs make them favorable for constrained environments like ships or nuclear power plants. Unfortunately, interest in developing supercritical CO2 closed-cycle Brayton systems petered out. Open-cycle systems were more mature, with far higher temperatures and efficiencies. Closed-cycle systems were still working out their technical issues. And inside a terrestrial thermal power plant, the technology's potential size advantages were not all that relevant. Fossil fuels also generate higher temperatures, which more favors steam turbines or helium Braytons. Fortunately, the technology was found to hold interesting potential for nuclear energy. Nuclear power plants share similar technical traits with fossil fuel thermal plants, as in they both heat up water to turn a turbine. But their economics are quite different. A fossil fuel plant's biggest operating cost is that of the coal or oil fuel. So utilities add certain complexities to their steam turbines, like reheat cycles, to squeeze as much energy as possible out of their coal. I said this earlier. But with nuclear energy, the cost of the uranium fuel is small compared to the plant's immense upfront cost. About 30% of that is the turbine. So the supercritical CO2 turbine's potential simplicity and smaller size can impact those build costs. There are also potential safety benefits with a closed-cycle turbine, as the sealed cycle could possibly prevent the accidental release of any fissile material. In 1970, Ferrer collaborated on a small 150 kilowatt electrical supercritical CO2 loop. Not a full turbine, but a loop, evidently to investigate its use for nuclear energy generation, so people recognized the potential very early on. The problem that people hit at the time was that supercritical CO2 turbines achieved their ideal thermal efficiency with inlet temperatures of about 550 degrees Celsius. But the light water reactors of the 1960s and 1970s produced temperatures between 200 to 300 degrees, so short of what was ideal. The technology gained new energy in the late 1990s and early 2000s due to a general revitalization of nuclear energy thanks to high oil prices and U.S. government support. Technology changes also played a factor. New energy sources were emerging, most notably the generation for nuclear reactors, stuff like the molten salt reactor or very high temperature reactor. These can achieve temperature ranges of about 550 degrees Celsius or higher, which is the turbine's sweet spot. Researchers also identified synergies with the small modular reactor. the ever-so-memed SMR. SMRs are smaller advanced fission reactors with power capacities under 300 megawatt electrical, but can be prefabricated in a factory and integrated into a site. Supercritical CO2 turbines jive with the SMR's overall goals for simplicity, smaller size, and lower capital costs without compromising too much on thermal efficiency. Supercritical CO2 technology is not alien. The oil and gas industry already compresses and pumps carbon dioxide, so there is a precedent. But there are major technical challenges, perhaps the most foreboding one being understanding and handling the changing physical characteristics of the carbon dioxide as it transitions inside the turbine machinery. Small changes in gas temperature and pressure can lead to big changes in the CO2's density, viscosity, and compressibility. This has major consequences on the machine's components like its compressor, which tend to be designed for fixed conditions. The supercritical carbon dioxide flowing through the turbo machinery is dense, putting immense loads on the machinery's bearings and seals. Broken seals cause leaks and what are called windage losses, significant efficiency losses that can be as large as 2% of thermal efficiency. Another challenge concerns the turbine's materials, same as with advanced steam turbines. Metals have to maintain their integrity in a high heat environment over the 30 or so years of its lifetime. Studies on how stainless steel and nickel alloys will perform in such conditions are limited. Risks include carburization, where carbon diffuses into the metal, sensitization, where carbon reacts with steel elements like chromium, as well as high-temperature corrosion and erosion. There are a lot of supercritical CO2 turbine projects around the world. We've been developing this stuff since the 1960s, remember. The first post-2000 projects began in the United States with collaborations between MIT and national government labs like Sandia. Many were test loops that were too small to show the true physics and mechanics of scaling to commercial size. After 2015, Sandia realized that they needed to go bigger, and they sponsored projects to build a 10-megawatt electrical turbo machine power system, hoping that one of these machines fulfill a non-nuclear commercial use case. Some of these designs have been called ingenious, including one where the turbine rotors, the compressor, and the recompressor are all assembled on one shaft. This project, referred to as 10-megawatt electrical supercritical transformational electric power, or STEP, eventually built a pilot plant in Texas. In the end of 2024, it recently finished Phase 1 testing, generating electricity for the first time. There are also multiple startups. A notable one is EcoGen. Founded in 2007, they partnered with turbine maker GE Vernova to produce some of the first commercial supercritical CO2 power loops. They're selling waste heat to power systems, which convert waste heat from industrial sources like gas turbine exhaust for extra electricity. They lack a combustor and all, but do use supercritical CO2. I say it counts. Others include Net Power, which is working on a practical alum cycle, Arbor Energy, which recently raised $55 million in a Series A, and Peregrine Turbine Technologies, which is making modular turbines for any heat source and has little to do with birds. Shifting to things abroad, there are major projects across Asia and Europe as well. The South Koreans and Japanese are building turbines at Korea Institute of Advanced Science and Technology and the Tokyo Institute of Technology. Both are pretty advanced, but have hit upon challenges relating to seals and components. The Chinese only recently initiated technology development but are advancing rapidly. In December 2025, they opened what they called the first commercial supercritical carbon dioxide power generator at a steel plant called Chaotan 1. It generates power from waste heat in the steel plant. And the Europeans are working on this as well. Their CO2OL heat project is building a CO2 turbine to harvest waste heat from a cement plant in Czechia. I love Czechia, the country, so I was pleased to learn this. And something else that caught my eye is Solar SCO2OL, a European technology development project that seeks to use supercritical CO2 turbines for solar thermal systems. These focus solar energy into heat, which can then be used to warm up a working fluid to do work. The idea behind this project is to help such solar thermal power plants become more economical. In the end, the turbine's key compelling benefits are clear, in that it can offer high thermal efficiencies in a way smaller package. The potential is there, but there is something to be said that the core academic principles of the technology have been largely developed since the 1970s, and we still don't have a full live system in a commercial environment. It seems that, for all of its failings and inefficiencies, the steam turbine spins on because it is massive, relatively forgiving, and has 140 years of proven history behind it. For the supercritical carbon dioxide turbine, on the other hand, the sweet spot seems to be as before: small is beautiful, but the engineering and materials issues are intimidating. I hope they eventually figure it out. Alright everyone, that's it for tonight. Thanks for watching. Subscribe to the channel, sign up for the Patreon, and I'll see you guys next time.